Alright, so in this section we are going to go and start talking about functions and their graphs. In the last section we discussed y is a function of x, which just meant basically write something in terms of y equals, but we didn't really define what a function was. So we called, back in Algebra 1, every input had a unique output, or every domain had its own unique range. The technical definition in calculus is a function of a set D to a set R is a rule that assigns the unique element R to each element in D. The vertical line test is obviously the graphical interpretation of this definition. Vertical line test, again, is just where you draw that line straight up and down, and if it touches more than one point, for example, then this would not be a function. So that vertical line can touch one point and only one point. That's it. Alright, so there are 3 domain restrictions that we must continue to be aware of throughout this course. I know I heavily emphasized 2 of them last year. The first one was that the denominator cannot be 0. If we divide by 0, our brain goes boom, it's a bad time. Alright, that second one that we talked about last year was that underneath the square root cannot be negative in even roots. So the variable in even roots we're going to try to spell negative again. So I usually just use square roots because square roots are the most common, but fourth roots and sixth roots and every single even type of root must have a positive number underneath its radical. And the third one that we didn't really get to talk about too much was that a variable inside of a log actually must be positive as well. So logarithms don't work if you have a negative base, and we'll look at graphs here in a little bit. So the other thing that we talked about last year quite a bit, especially in the first semester pre-calculus, was intervals. We talked about being included, excluded, brackets or parentheses, that type of thing. I don't remember if we didn't go ahead and look at these graphically or not. I think we did, but that doesn't mean that we did. I could just be imagining things. So open intervals, I usually represent those with open circles versus closed intervals. I end up having a closed circle. So if I'm trying to use interval notation and inequality notation to look on the interval of the x-axis below, I'm saying that my x is in between a and b here. So I look and I see x is in between a and b. However, a is not included because it's an open circle. B is not included because it's an open circle. So last year with interval notation, we said, hey, it was on the interval of a to b. Neither one of those are included. So I went ahead and I put parentheses. Back in Algebra 1, maybe some Algebra 2 in there, you guys actually did that notation with inequalities. So you would have said, hey, I've got an x, it's between a, it's between b. Neither one of those are included. So I would not have an or equal to bar. Cool, we move on with our lives. X again is between a and b. This time a is not included, b is included. So it's from a to b. A is not included, so it gets a parenthesis, versus b is included, so it gets a bracket. Alright, again, x is between a and b. A is not included, so it does not get that or equal to bar. But b is included, so we do go ahead and put that or equal to bar, because it could possibly be at b. Alright, looking at, I guess I would call it example C most of the time. We've got this weird stuff going on. It's on A to B, and then we've got this gap in the middle, and then we go from C on and on and on. So what that means is I've got my x between a and b. All right. So a this time is included. It does have that full circle versus b does not. And then we have a gap. So it could be or x is from c, which is not included, on forever. And last year we represented that with infinity because it goes on and on and on, kind of like I do sometimes. Or we could say, hey, x is in between a and b. This time a is included, so it does get that or equal to bar. Or x is greater than c. Interval notation is a lot more common, though, especially in that type. And then finally, we've got example D, I guess, from B onwards. The only thing is we're not going to include C. So how I would write that in interval notation, I would literally say, okay, I've got from B to C, but C is not included, so I have to note that somehow, some way. So I've got to say, hey, union with C to infinity. Just saying, hey, it includes everything except for C, which is why there's that weird overlap there. All right, picks up where it left off. All right. Moving on, there are mostly 12 main graphs that we need to be aware of. Usually it is y equals x squared, y equals the square root of x. Occasionally that y is equal to 1 over x. Definitely the y equals absolute value of x. Sometimes the stair step is involved, but I don't really see that one too much anymore. Exponential decays and exponential growths are usually just under one big one of the 12. Logarithms are pretty important. Sine of x, cosine of x, and tangent of x that we talked about last year are usually part of that big 12. If you don't remember what these graphs look like, let's head on over to Desmos for a second, check them out real quick, see what's going on with them, and then I'll come right back. Alright, so y equals x, that one we should all be familiar with from Algebra 1. It's just a straight line, passes through 0, 0, 1, 1, etc., etc. I'm going to back out just a little bit so people can actually see, especially once I go to other functions. I've got y equals x squared, which should be that family-friendly parabola. It goes on and on. 0, 0, 1, 1, 2, 4, etc., etc. X cubed isn't one of the big 12. However, it is listed in the notes. So x cubed kind of looks like a parabola that got flipped on its head. However, it's an odd function. It has an odd exponent, so that part makes sense. So it's symmetric about that origin, or symmetric about the line of y equals x, which we'll get to here in a minute. One of the big 12, this is literally half a parabola turned sideways, y equals square root of x. So you've got 1, 1, 4, 2, 9, 3, etc., etc. Y equals 1 over x. Alright, so you got horizontal asymptotes and a vertical asymptote going on. On this one, we talked about those a little bit last year. The less common one is that y equals 1 over x squared, which is a little bit fun to see. It definitely has a vertical asymptote still and a horizontal asymptote still, but you don't see anything below that x-axis, which is kind of cool to play with. The next one is that y equals absolute value of x. It can be written in those bars, or it can be written as ABS. Both of them mean the same thing, but that's just that value. Whoops. The next one that we're going to take a look at is logarithms. We didn't get to look at those graphs too much last year. Again, if my base is anything less than 0, it will not appear. Even if I zoom out forever and ever and ever, it is not going to start appearing until, if I make B even at 0, it doesn't appear. But as soon as I start to make it a positive, oh look, something happened. And this is what we call a logarithm. Q, Q, Q. So they are the inverses of exponential functions, which I will have to go and see here in a second, because I could not get those to work on Desmos, which is perfectly fine. Sometimes that happens. Graphing calculators most of the time work, but for some reason Desmos just doesn't like it. So again, I'll show you that. Actually, I can show you guys that now. Exponential growths is that when b is greater than 1, it grows really, really fast. It shoots up. We like to see that in the stock market. Versus an exponential decay. I don't really like to see those when I'm looking at my stocks. That's just when b is in between 0 and 1. B being my base. Going back to Desmos now. We're trying to. Alright, other functions that we got familiar with, especially last year, was this basic sine function, which is that squiggle that goes on forever. And I only made you guys graph a period of these, but we should still be familiar with what it looks like, because it literally goes on and on and on and on and on as just one big squiggle. Cosine, very similar. Couple things. Please do remember that one of them starts at 0, 0. The other one does not. So if you need to go back and look at those notes from pre-calculus, please do that. That is going to be vital this year. And then the one that I didn't make you guys graph a whole bunch was that tangent that almost looks like a cubic function over and over and over again. This one's not as important to memorize. However, I do need you guys to know where tangent crosses, where that the asymptotes are, and where your other two main points are. So again, if you need to go back, find those graphs, see where those main points are, please do that. That needs to get refreshed. I will start giving unit circle quizzes relatively soon, if not tomorrow. Okay? So those are the main graphs. Let's hop on back over to the notes. Alright, so let's talk